Hi students, today the topic is cerebral circulation. The learning objectives are about the cerebral blood vessels, characteristic features of the cerebral blood flow, measurement of the cerebral blood flow, regulation of the cerebral blood flow and its applied aspects. Now first coming to the cerebral blood vessels. So we have to see about the arteries and veins of the brain. These arteries are derived from two internal carotid arteries and one basilar artery. This basilar artery is formed from union of two vertebral arteries. And through the circle of Willis, they will supply the entire brain. The circle of Willis is a free anastomosis between the two internal carotid arteries and two vertebral arteries. This will equalize the pressure on the arteries of the two sides. So what is the main purpose? It should equalize the pressure on the arteries of the two sides. In this way, the circle of Willis allows the blood that enters by either internal carotid artery or through the vertebral artery to be distributed to any part of the both sides of cerebral hemispheres. 6 large arteries that will actually take part in the formation of circle of Willis. They will supply blood by their central branches and cortical branches to the brain substance. See this? These are the two vertebral arteries forming basilar artery. And it is giving posterior cerebral artery. Two posterior cerebral arteries. And this is internal carotid artery. Two internal carotid arteries. They are joined by posterior communicating artery to the posterior cerebral artery. And together are joined by, that is, two internal carotids are joined by anterior commissure artery. Okay. So these are the two posterior cerebral arteries, two posterior communicating arteries, two internal carotid arteries and two anterior commissural arteries. This is the circle of Willis. We will discuss a few points about blood-brain barrier and blood-CSF barrier here. The detailed discussion will be of this content will be present in another video. First coming to the blood-brain barrier. This blood-brain barrier restricts the movements of large molecules and highly charged ions from the blood into the brain and spinal cord. So what is the most important function of the blood-brain barrier? It will restrict the movement of large molecules and highly charged ions from blood into entering into the brain and spinal cord. Now this blood-brain barrier is formed by central nervous system capillary endothelial cells and their intercellular junctions. So the endothelial cells, capillary endothelial cells and their intercellular junctions will form this barrier. And this is lacking vesicular transport also. So there is no vesicular transport here. So most substances that must cross the blood-brain barrier are not lipid soluble. So they have to cross the barrier by specific carrier mediated transport system. So if any molecule to be crossed through the barrier, it should have a specific carrier. So with the help of specific carrier mediated transport, they will be carried inside the cell. For example, water is carried through aquaporin 4 and glucose is transported through GLUT1. Now coming to the blood CSF barrier. The capillaries that transverse the choroidal plexuses, they are freely permeable to the plasma solutes. However, a barrier exists at the blood CSF barrier. It exists at the level of the epithelial cells that make up the choroidal plexuses. Okay, this is the choroidal capillary blood. Actually, the endothelium of this is freely permeable to the plasma solutes. Here you have epithelial cells. It is forming a blood CSF barrier. This is CSF. So it is forming blood CSF barrier. This barrier is responsible for carrier mediated active transport. So here also you need a carrier to transport any material from here to here, CSF. Whereas here blood brain barrier, this is the brain capillary blood. This is the endothelium of the capillary which forms a tight junctions. Okay. Now coming to the venous drainage. The cerebral hemisphere has two sets of veins. They are superficial and deep veins. The veins draining the brain, they will open into the various dural venous sinuses. So within the dura you have venous sinuses. So these veins will open into the dural venous sinuses. So what happens ultimately? The blood from all these sinuses reaches the sigmoid sinus. Then the sigmoid sinus will enter into the internal jugular veins. That's how the venous drainage happens in the cerebral hemisphere. Now coming to the characteristics of the cerebral blood flow. So what are the important characteristics of the cerebral blood flow? The brain relies on continuous blood flow. Okay, the brain should get blood flow continuously. It is the most susceptible organ to ischemia. So it cannot resist ischemia. If there is no blood supply for about 5 to 10 seconds, then there will be loss of consciousness. And if there is no blood supply up to 3 to 4 minutes, then it leads to irreversible brain damage. What is a normal blood flow? The brain should get 15% of the cardiac output. That is 750 ml per minute. Okay. So what is the cardiac output? 5 liters. 15% is equal to 750 ml per minute. If you take per 100 grams of tissue wise, it should have 50 to 55 ml blood per 100 grams of tissue per minute. Average weight of the brain is 1400 grams. Okay. So if you take the out of cardiac output, it requires 15%. That is 750 ml is required per minute. Per gram, if you see 50 to 55 ml blood it requires per 100 grams of tissue per minute. Average weight of our brain is 1400 grams. Okay. Now coming to the normal oxygen consumption of the brain. It takes 3.3 ml of oxygen per 100 grams of tissue per minute. Okay, so it wants 3.3 ml of oxygen per 100 grams of tissue per 1 minute. Okay, so totally it requires 50 ml of oxygen per minute. And the oxygen consumption of gray matter is more than the oxygen consumption of the white matter. Mainly the oxygen is coming from the glucose molecule. And the glucose uptake is 5.5 milligrams per 100 grams of the brain tissue per minute. So what is the glucose uptake? It will take 5.5 milligrams of glucose per 100 grams of brain tissue per minute. And the respiratory quotient here is 0.95 and 0.99. Now coming to the distribution of the blood. We know that the major arteries anastomose by the circle of Willis. Okay, these circle of Willis will give branches, central branches and cortical branches. The central branches are end arteries. Okay, so there is no communication between the central branches. Now coming to the cortical branches, they form border zones. These zones are susceptible to form watershed infarcts. Okay, so the central branches, you know that they are end arteries. Okay, that is they do not anastomose with each other. So what happens? Therefore, any thrombosis or rupture of these vessels, they will lead to infarction. Coming to the cortical branches. What about cortical branches? They are anterior, middle and posterior cerebral arteries supplying the surfaces of the hemispheres. Okay. So they are supplying the surfaces of the hemispheres and they will form border zones between the areas which are supplied by these arteries. So why we are discussing about these areas? Because these border zones are susceptible to ischemic damage. Okay, ischemic damage. Uh, and here the blood supply is also very low. And there is it is having inadequate blood supply. These areas are called watershed infarcts. We have two watershed infarcts, anterior and posterior. Anterior watershed infarct results in inadequate perfusion of the border zone between the supply of anterior and middle cerebral arteries. Okay, and it is characterized by development of contralateral hemiparesis of the leg and some language defects and behavioral changes. Then, whereas posterior watershed infarct, it results due to inadequate perfusion of the border zone between the supply of middle and posterior cerebral arteries. And if it is there, the infarct is there in that area, it will lead to partial visual loss and also leading to some language problems. Now coming to the measurement of blood flow. So how to measure cerebral blood flow? How much the blood is going into the cerebral circulation? So we can measure the cerebral blood flow by CATI method, by SPECT method, that is radioactive, by using radioactive substances, that is SPECT, that is single photon emission computed tomography. So that is a SPECT that will use radioactive substance. And with the help of PET, that is with the help of positron emission tomography, and also with the help of MRI, that is magnetic resonance imaging. Okay, so with the help of these four methods, we can measure the cerebral blood flow. What are those methods? CATI method, SPECT method, PET method and MRI method. So first coming to the CATI method. This CATI method is based on the fixed principle. Okay, this CATI method is based on the fixed principle. So how to do this method? So what is the first I have to see some points about the fixed principle. So what is this fixed principle actually? It states that the amount of substance taken up by an organ per unit of time, it is equal to the arterial level of the substance minus venous level of the substance multiplied with the blood flow. That is, the equation is actually Q is equal to A minus V multiplied with F. So what is Q here? That is the amount of substance taken by an organ per unit of time, that is Q. That should be equal to A minus V, that is the concentration of the substance in the arterial blood minus concentration of the substance in the venous blood. This difference should be multiplied with the blood flow, that is F. Okay. So, when this principle we can apply, this principle is applicable only in situations in which the arterial blood is the sole source of the substance taken up. Okay. The fixed principle, it can be used to measure many outputs like cardiac output, cerebral blood flow. Okay. So our Ketty method is also based on the fixed principle. How to do this method? That is, what is the procedure? In this method, the subject is asked to breathe a mixture of the air that is composed of 15% of N2O, that is nitrous oxide, for 10 minutes. So he has to breathe 15% of N2O, that is nitrous oxide, for 10 minutes. During this period, what we should do is serial samples have to be taken for every minute from the internal jugular vein. From where? From the internal jugular vein, and also from a peripheral artery. So this internal jugular vein represents the venous blood from the brain. So actually the internal jugular vein, we have seen that all the venous blood is collecting into the internal jugular vein. So this represents venous blood flow from the brain. And also we have to take blood samples from the peripheral artery. So the cerebral blood flow can be calculated by this formula. What is that formula? CBF, that is cerebral blood flow, is equal to nitrous oxide taken up by the brain tissue per minute divided by arteriovenous difference of nitrous oxide concentration. Okay. So we can get the cerebral blood flow. What is the formula? Nitrous oxide taken up by the brain tissue per minute divided by arteriovenous difference of nitrous oxide concentration. But the disadvantages of this technique are, what are the disadvantages? It will give an average value, but no information about the regional differences. So overall value it will give, not about the regions of the brain. We cannot say if the CBF is low. We cannot say from which part of the brain the actual blood flow is not happening. Okay, so overall value it will give, not the regional values of the brain. Okay, understood? So it gives the average value, but no information we can get about the regional blood flow. For example, if reduction in the blood flow of any one part of the brain, it may be completely compensated by an increase in flow in other part of the brain. So what happens? The CBF remains the normal. Okay, so actually we are having damaged, that is infarcted area, but it cannot detect. And second point is, it measures the blood flow to only perfused areas of the brain. So this is the second disadvantage. It will measure the blood flow to only the perfused areas of the brain. And what is the third point? It can be used only in the steady state conditions and not for the measurement of rapidly changing blood flow. Okay, so these 3 points are the disadvantages. What is the first point? It will give average value, not about the regional value. And it measures the blood flow to only perfused areas of the brain. And it can only be used in steady state conditions. It cannot measure in conditions like rapidly changing blood flow. So this is the Ketty method. Now coming to the second method, that is SPECT method. It will use radioactive substances. What is SPECT? Single photon emission computed tomography. Now what is the principle lying here? In the Ketty method we have fixed principle. In SPECT method, what is the principle? In this technique, the blood flow to a region of the brain is measured from the clearance curve of an inert radioactive tracer. So, we are giving an inert radioactive tracer and we are seeing, measuring the how much time it is taking to clear the radioactive tracer from this area. What are those inert substances we can use? Xenon 133 or xenon 123. Okay. So what is the procedure here? What is the procedure? So commonly we are using xenon 133 or xenon 123. A known amount of this xenon in a gas form. It is present in the gas form. It should be dissolved in a known amount of saline. Okay, so it should be dissolved in a known amount of saline and it should be injected in the internal carotid artery. Okay, internal carotid artery within 1 to 2 seconds. So what we are doing? We are taking this gas and we are dissolving it in a saline solution. Then we are injecting it into the internal carotid artery rapidly, that is within 1 to 2 seconds. Then the arrival and clearance of the tracers is detected for 10 minutes by multiple collimated scintillation detectors built into a helmet that fits over the cranium. Okay, so over the person's cranium we will fit detectors. Okay, so these are the multiple detectors. They will work on the collimated scintillation technology. So they are called multiple collimated scintillation detectors. They will detect this for 10 minutes after injecting into the internal carotid artery. Each detector is collimated to scan about 1 centimeter square area of the brain surface. So each detector can detect up to 1 centimeter square area of the brain surface. Then the output will be given from the detectors. Okay, the output from the detectors is processed in the computers and displayed on a colored television screen. The color is proportional to amount of blood flow. Okay, so the color we have to see. The color is proportional to the amount of blood flow. And the resolution can also be improved by computerized tomographic reconstruction. So this resolution can also be improved by CT technique. So now how to calculate the CBF from this? CBF, cerebral blood flow, okay, is equal to lambda B multiplied with H max minus H10. The whole thing is divided by A10. This lambda B is brain blood partition coefficient. H max is maximal height of clearance. H10 is clearance height at 10 minutes. And A10 is area under clearance curve. Okay. So we will get this cerebral blood flow in ml per gram per minute. So what we are doing? We are first dissolving the xenon gas, inert radioactive xenon gas in the saline, and we are injecting rapidly into the internal carotid arteries. Then we are putting the detectors over the cranium. Each detector will detect 1 centimeter square area of the brain surface. And the output is processed in the computer and it is coming out in the form of a color coding in the television. So depending upon that we are getting the CBF, that is cerebral blood flow, in ml per gram per minute in this formula. What is that formula? lambda b multiplied with h max minus h10 divided by a10. So we are drawing a curve, that is clearance curve. So that whole area under the clearance curve comes under a10. And lambda b is brain blood partition coefficient. H max is the maximal height of clearance of the xenon. And h10 is the clearance height at 10 minutes of the xenon. Okay. Now what is the advantage of this technique? So what is the advantage? We can detect the blood flow to different regions of the cerebral cortex. Okay. So different regions, how much their blood is going to the different regions of the brain, we can calculate. That is the main advantage of this technique. Now coming to the third one, that is PET, positron emission tomography. It can also be employed to measure regional cerebral blood flow. So with the help of this also, like SPECT, we can measure the regional cerebral blood flow. Here what we are using? Short half-life radioactive isotopes we are using, like fluorine 18, oxygen 11 and oxygen 15. F18, O11 or O15. We are using these substances. And these substances are attached to one glucose compound. What is that? 2-deoxyglucose. So this or this or this will be attached to 2-deoxyglucose. Then we are injecting this material into the subject, same as a spectre. Okay, so we are dissolving these substances and we are injecting into the artery. Now the arrival and clearance of the tracer is detected by same scintillation detectors placed over the head. So in this also we will place scintillation detectors over the cranium of the person, and they will receive the data from the cerebral arteries, that how much of the amount is coming and how much is leaving. So how much is coming from the arteries and how much of the amount is leaving from the veins, they will detect. So it will give. So what is the main thing, that 2-deoxyglucose will be taken up by the brain tissue. Okay, the local uptake of this glucose molecule is a good index of the blood flow, and its concentration in different parts can be easily monitored. So these detectors will detect how much is the glucose present in the arteries and how much it is present in the veins, and so difference of these two will give the utilization of the glucose. Like that, it will detect the amount of blood flow in the particular region. Then coming to the fourth one, MRI, magnetic resonance imaging. In this technique, regional concentration of the individual metabolites is measured. Okay, and changes in the local oxygen utilization are mapped, from which regional cerebral blood flow is studied. So what is the advantage of this? Here also we can measure the regional blood flow. So but this will not utilize any radioactive isotope. So this is another advantage. It is not using any radioactive isotope. Then how it is working? In this technique we are using a magnetic field. Okay, so this technique is based on detecting signals from different tissues in a magnetic field. And you have another term called fMRI, that is functional MRI. It measures the amount of blood flow in a tissue area. So during activity, what happens? The local blood flow and oxygen utilization will be increased by that particular tissue. Therefore, when the neural activity increases, there is an increase in discharge activity that changes the field potentials. The fMRI detects increase in the oxygenated blood. So what is the advantage of fMRI? It doesn't involve use of radioactive isotope activity. So we can use at frequent intervals to detect the regional brain blood flow changes in the same individual during different types of activity. So for example, we can detect what is the blood flow of the brain in the awake state, or what is the blood flow during sleeping state, and if the person is any solving any problem like mathematical problem, so what is the blood flow to the cerebrum. We can detect all these things with the help of this functional MRI. So we are discussing the measurement of cerebral blood flow by four methods. They are KT method, SPECT method, PET method, MRI method. KT method is based on fixed principle. In this, nitrous oxide is used. Second one is the SPECT method. In this, radioactive isotope like xenon 123 or xenon 133 is used. In the PET, we are using fluorine F18 or O11 or O15, which is attached to 2-deoxyglucose. So in SPECT and PET, we are attaching scintillation detectors to the cranium of the person. Then coming to the MRI. MRI will use magnetic field, and it is detecting the brain's activity by brain's cerebral circulation by the utilization of the oxygen. So if the person is active, then he will utilize more amount of oxygen in that particular area. So with the help of SPECT, PET and MRI, we can detect the regional blood flow, and with the help of MRI, we can also detect the cerebral blood flow changes in activity of sleep, awake state, or any problem solving state. And the most important thing is it won't use any radioactive isotope. So we can use it at frequent intervals. That is about the measurement of cerebral blood flow. Now coming to the regulation of the cerebral blood flow. How the cerebral blood flow is actually regulated. So it is by different mechanisms. What are those mechanisms? By metabolic regulation. So metabolites means what? Carbon dioxide, oxygen and some ions. Okay. So that is about metabolic regulation. And also it can be regulated by autoregulation. Autoregulation of cerebral blood flow. And the third thing is role of the intracranial pressure in the regulation of cerebral blood flow. In that we will discuss about two things, Monro-Kelly doctrine and Cushing reflex. And fourth one is the nervous regulation of the cerebral blood flow. Okay, so there are four regulations: metabolic, autoregulation, role of intracranial pressure, and a nervous system regulation. So first coming to the metabolic regulation. First, metabolic regulation. In the metabolic regulation, we are discussing carbon dioxide regulation. Okay. So, how carbon dioxide is regulating? Physiologically, this partial pressure of carbon dioxide, that is PCO2, is the most potent vasodilator of the cerebral blood vessels. Okay. So, this is the first point you have to remember, that this partial pressure of carbon dioxide is the most potent vasodilator of the cerebral blood vessels. With an increase in the PCO2 in the blood, there will be increase in the cerebral blood flow linearly. Okay, linearly. However, when the arterial PCO2 touches the 80 mmHg or it increases above the 80 mm of a mercury pressure, then what happens? There is no further increase in the cerebral blood flow. Because why? Because maximum dilatation of the blood vessels already happened. So there is no further dilatation of the blood vessels, no further increase in the cerebral blood flow. Similarly, what happens when arterial PCO2 falls below 20 mmHg, there occurs no further decrease in cerebral blood flow because the cerebral blood vessels have already constricted to its maximum. Okay, so between 20 to 80, there is a linear increase in the cerebral blood flow when the PCO2 increases in the blood. So in this figure, you are seeing dotted line and a continuous line. What is this dotted line is telling about? When the arterial PCO2 is increasing, okay, uh, from very less level, that is from some 20 mmHg of PCO2 to 70 to 80 mmHg of PCO2, what is happening? The cerebral blood flow is linearly increasing. Now, what is this continuous line? At arterial pressure of PCO2 is 40 mmHg, that is normal. Then what happens? If you increase the arterial pressure, okay, if you increase the blood pressure, then up to 60 mmHg, it is increasing, that is cerebral blood flow. Then between 60 to 140 mmHg, because of auto regulation of the cerebral blood flow, the cerebral blood flow is not increasing, although the blood pressure is increasing. Then after it is crossing 150 or 140 millimeter of mercury blood pressure, then it cannot have auto regulation also. Then the cerebral blood flow is increasing. So this graph includes two mechanisms, that is, it is showing arterial PCO2 with the cerebral blood flow, and it is showing a blood pressure with the normal arterial PCO2 with the cerebral blood flow. Now coming to the partial pressure of oxygen, how it is affecting. So in the PCO2, if you increase the PCO2 of 1 mmHg above the normal range, it increases the blood flow by 3 ml per 100 grams per minute. Okay. And if you decrease the PCO2 of 1 mmHg below the normal range, it decreases the cerebral blood flow by 1.5 ml per 100 grams per minute. Okay. Then coming to the actually we have mixed the pH with the carbon dioxide. The effect of carbon dioxide is mediated via the change in the pH. Okay, if you raise the partial pressure of the carbon dioxide, what happens? The H plus ions also rise in the blood. Now the carbon dioxide will easily diffuse through the blood-brain barrier and reaches the CSF. In the CSF, what happens? This carbon dioxide combines with the water and will form H2CO3, that is carbonic acid. And this H2CO3 will dissociate into H plus ions and HCO3 minus ions. The H plus ions will induce the cerebral vasodilatation. Okay. So this is the mechanism by which carbon dioxide is causing cerebral vasodilatation. So because these H plus ions cannot cross the blood-brain barrier. Okay. So carbon dioxide has to go inside the CSF and it will be combined with the water and it should form carbonic acid, and then it should dissociate, and H plus ions will cause this effect. So if there is any substance that increases the acidity of the brain, that is, it increases the H plus ion concentration in the brain, what it will cause? It will cause cerebral vasodilatation and it will increase the cerebral blood flow. So some substances are lactic acid, pyruvic acid, or some other acidic compounds which are formed from metabolism. They will cause cerebral vasodilatation. Now coming to the partial pressure of oxygen, how it will affect the cerebral blood flow. Slight fall in partial pressure of oxygen causes vasodilatation and it increases the cerebral blood flow. Okay. So if there is a fall in PO2, then there is a vasodilatation. Any stimuli which either reduces the oxygen supply to the brain or increases the oxygen need of the brain, it results in rapid formation of adenosine. It is a potent dilator of the bile arterioles. So, in the carbon dioxide, if carbon dioxide increased, H plus is formed, it is causing vasodilatation. If oxygen is consumed more, it leads to the formation of adenosine, it will dilate the arterioles. Inhalation of the hyperbaric oxygen causes cerebral vasoconstriction and it will decrease the cerebral blood flow. High cerebral PO2 disrupts the neuronal metabolism and produces convulsions, coma, and death. Okay. So, while giving hyperbaric oxygen therapy, we should be cautious because it will cause vasoconstriction and disturbances in the neuronal metabolism and ultimately leading to convulsions, coma, and death also. Now coming to the potassium ions. So, these potassium ions are also involved in the regulation of the CBF. If you increase the potassium ions in the CSF, how to increase? After the hypoxia or electrical stimulation of the brain and seizures. So after hypoxia, after electrical stimulation of the brain and after seizures, it will release to it will cause release of potassium in the CSF. And this potassium causes rapid increase in the cerebral blood flow. Okay. So, but one thing is this potassium is not increased in the sustained level throughout the period of the stimulation. So, if you are stimulating the brain with an electric stimulation for some time, the potassium is not raised throughout that time. Only the initial increase in the cerebral blood flow is attributable to the release of potassium ions. So, immediately after you give the electric stimulation of the brain, potassium will be released from the CSF and they will cause increase in the cerebral blood flow. Now coming to the second regulation, that is auto-regulation of cerebral blood flow. Auto means self. So due to auto-regulation, the cerebral blood flow remains nearly constant between 60 to 140 mm of blood pressure. So if the blood pressure is this graph we have already seen in the previous graph. So that is previous graph is a combination of the two, that is auto regulation and regulation of the blood flow by partial pressure of carbon dioxide. So if you see this between 60 to 140, there is no increase in the cerebral blood flow if you increase the blood pressure also. But when the blood pressure falls below 60 mmHg, the cerebral blood flow is extremely compromised and the patient may go into syncope also. So when the blood pressure is above 140 mmHg, what happens? There is more amount of cerebral blood flow and there is a disruption of the blood-brain barrier. Okay. So it leads to cerebral edema and cerebral hemorrhage. So both ends are very dangerous. If you go below 60, it will lead to syncope. If you go, that is below 60 mmHg, if you go above 140 mmHg, it will lead to cerebral edema, cerebral hemorrhage. Okay, so the cerebral blood vessels will stretch and they will rupture and it will cause hemorrhage and edema. So both extremities are dangerous to the cerebral circulation. So this control of blood flow during alterations in blood pressure, that is autoregulation. This autoregulation is mainly because of the two mechanisms, that is two theories have been put forward to explain how autoregulation will happen. Those are myogenic theory and metabolic theory. So are these first some points. This autoregulation is the ability of an organ or tissue to adjust its vascular resistance and maintain a relatively constant blood flow over a wide range of arterial pressure. So that particular organ or tissue should maintain, okay, constant blood flow irrespective of the alterations in the blood pressure. This is accomplished by a change in the resistance which is proportionate to the changes in the arterial pressure. So how it is how it is maintaining the constant blood flow? By changing its resistance. This change is also should be proportionate to the changes in the arterial pressure. Autoregulation is well developed in the kidney, brain, heart, skeletal muscle and mesenteric circulations. Two theories I have told to explain the phenomenon of autoregulation. Those are metabolic theory and myogenic theory. And this autoregulation can be abolished easily by trauma, hypoxia, and any other noxious stimuli. In such states, what happens? The flow and apparently the pressure in microcirculation increases with an increase in cerebral perfusion pressure. So, if you increase the blood pressure, the cerebral blood flow is also increasing if autoregulation is abolished. So, this mechanism of autoregulation is important. Metabolic and myogenic theories of autoregulation. Okay. In metabolic theory, the main regulating substance is a partial pressure of carbon dioxide that we have already seen. So, how partial pressure of carbon dioxide is affecting? If you increase the partial pressure of carbon dioxide, it will increase the cerebral blood flow by causing increase in the H plus ions in the CSF causing vasodilatation. Okay. So, in the metabolic theory, we are considering the carbon dioxide mainly through H plus. Okay. Then, in the myogenic theory, what is happening? The vascular smooth muscle responds to wall tension. Okay. So, this is according to law of Laplace. This myogenic theory is based on the law of Laplace. It is an increase in the arterial pressure. What it causes? It initially stretches the smooth muscle fibers in the vascular system. Okay. Then because of that stretch, what happens? The vascular smooth muscle will contract and return to the previous size. So that's how the muscle that is myogenic. What is that muscle? Vascular smooth muscle. How it is controlling the cerebral circulation. So an increase in the arterial pressure initially stretches the smooth muscle fibers. In response to that stretch, vascular smooth muscle contracts and returns the wall tension to the normal levels. The narrow lumen increases the resistance and compensates for the higher arterial pressure, returning the blood flow to control levels. So, this is now expanded, now contracted. Now, in the contracted state, we have higher resistance in the blood vessel. So, there is no increase in the blood flow. That's how it compensates the increase in the arterial pressure, returning the cerebral blood flow to the normal levels. That is myogenic theory. In metabolic theory, what we have seen? The increased blood flow because of increase in the partial pressure of carbon dioxide. What happens if the blood flow is increasing? It washes out the carbon dioxide rapidly. So all vasodilated substances like carbon dioxide, H plus, nitric oxide, adenosine. Okay, adenosine is increased because of decrease in the PO2. So adenosine, prostaglandins, and phosphate ions, potassium, and low oxygen levels in that area leads to adenosine formation. All these vasodilator substances are washed out because of the increase in the blood flow initially. As a result, what happens? The arterioles will constrict and again it will increase the vascular resistance and it will return the cerebral blood flow to the normal levels. So, what is the metabolic theory is telling? Initially, the blood flow is increased. Okay, initially the blood flow is increased. Okay, because of the increase in the perfusion pressure. This leads to washing out of the vasodilators present in the cerebral circulation. What are those vasodilators? Dilators? It may be potassium, phosphate, carbon dioxide, adenosine, nitric oxide, H plus, etc. Then washing out of the vasodilator will lead to constriction of the arterioles. Then, according to myogenic theory, first initially the blood flow is increasing if you increase the perfusion pressure. Then what happens? The vascular smooth muscle. So the smooth muscle which is attached to the vascular system, it is undergoing into a stretch condition. Then the stretched muscle will automatically contract and it will narrow the lumen, increase the resistance. Thus, these two theories are explaining how the autoregulation is happening in a system, that is in a cerebral blood flow system. Now coming to the third mechanism, that is role of intracranial pressure in regulation of cerebral blood flow. So intracranial pressure also regulates the cerebral blood flow by two mechanisms. One is the Monro-Kelly doctrine and another is the Cushing reflex. First coming to the Monro-Kelly doctrine. So according to this doctrine, what he is telling is the brain, CSF and blood which is present in the cerebral vessels. These are the three elements which are enclosed in a rigid cranial cavity. Okay, what are those three elements? The brain, CSF and blood in the cerebral blood vessels. These three elements are enclosed in a rigid cranial cavity. Then what happens? When any one of them increased, if any one of them is increased, then the rest of the two will be decreased. Okay. This relationship helps to maintain cerebral blood flow when changes in the arterial blood pressure occur at the level of the head. So these are important in the changes in the gravity. That is, when the body is accelerated upwards. So when we are going upwards in a lift, for example, we are experiencing positive G. So what happens in that condition? The blood moves to the feet level and arterial pressure at the level of the head decreases. And theoretically, what should happen? The cerebral blood flow should be severely compromised. But practically, it doesn't occur. Why it doesn't occur? Because the venous pressure and intracranial pressure are also decreased. And so, the pressure on the vessels is decreased. Thus, the blood flow is less severely affected. So, when we are going upwards, what happens? Blood is pulling in the feet, but actually we should go into syncope, but it is not happening. Why? Because the venous pressure, that is the pressure which is exerted on the veins, that is decreased. So the resistance is decreased in the brain blood vessel, so blood can easily flow in the brain, so it can get sufficient cerebral blood flow. That is one scenario. Coming to the second scenario, when the body is accelerated downwards, that is, we are experiencing negative G, we are coming down in the lift, the reverse should happen. Okay, the reverse will be occurring. That is what happens. The arterial pressure at the level of the head is much more increased. And what should happen? Our brain blood vessels should be ruptured because of that. But this is not happening. Why this is not happening? Because when we coming down, the intracranial pressure is also increasing. So the vessels will be pressed and the resistance will be increased. So there is not much flow in the cerebral blood vessels. So there is no rupturing of the cerebral blood vessels. So this Monroe-Kelly doctrine helps to explain how we can maintain the normal cerebral blood flow during our uh, gravitational changes, and how we can maintain our normal cerebral blood flow during our postural changes and during coughing and during Valsalva maneuvers also. Now coming to the second one, that is Cushing reflex. So here what happens when intracranial pressure is increased and becomes equal to the arterial pressure. What happens if our intracranial increased and equal to the arterial pressure? There is no blood flow. So it compresses the arteries in the brain and blood supplied to that particular part is severely decreased. In hypoxia and hypercapnia produced locally increases the discharge from VMC, that is vasomotor center. The resultant rise in systemic pressure tends to restore the cerebral blood flow. We will see it. So what is the basic thing? When the intracranial pressure is increased and when it becomes equal to the arterial pressure, that is SBP, systolic blood pressure, it should it will compress the arteries in the brain, and the blood supply is decreased in the entire brain area, mostly when the blood supply to the VMC, that is vasomotor center, is decreased. What happens? It leads to decrease in the oxygen supply to the VMC, that is hypoxia, and increase in the carbon dioxide accumulation in the VMC, that is hypercapnia, in the vasomotor center is happened. Okay, then the VMC discharges, that is the discharges coming from the VMC are increased. Then what happens? It will raise the systemic pressure to restore the cerebral blood flow. So the output from the VMC will increase the systolic blood pressure and it will increase the cerebral blood flow. So the rise in the blood pressure, that is systemic blood pressure, it is proportionate to the intracranial pressure up to a certain limit, beyond which it also cannot act, and cerebral circulation further ceases. So this effect, which protects the vital centers of the brain, is called Cushing reflex. The resultant increase in blood pressure also causes reflex bradycardia via baroreceptor response. Thus, bradycardia is an important feature of raised intracranial pressure. So, if the intracranial pressure is raised, there will be always bradycardia in that person. Why this bradycardia is coming? Because of the baroreceptor reflex. So, baroreceptor reflex itself is a single class. You cannot understand this now. So, basically what is happening? Increased blood pressure is causing decreased heart rate. Okay. So, because of the baroreceptor reflex. But Cushing reflex, why Cushing reflex is important? Cushing reflex protects the important areas of the brain uh, up to certain limit of the increase of the intracranial pressure. So, if the intracranial pressure is increased up to certain limits, the VMC discharges more. Because of the increase in the discharge of the VMC, the systemic blood pressure, the systolic blood pressure increases and leads to blood flow in the cerebral circulation. Uh, if the intracranial pressure is much more increased, then it can also cannot act. So up to one point only, the VMC can increase the discharge. That is, it can increase the SBP up to certain limit only. And one more is we can always notice bradycardia in the persons in which they are having the raised intracranial pressure. Then we are going to the fourth mechanism, that is nervous regulation of the cerebral blood flow. How the nervous system will regulate the cerebral blood flow. The cerebral blood vessels are innervated by noradrenergic vasoconstrictor fibers and cholinergic vasodilator fibers. So this is important. Noradrenaline, if it is released, it is causing vasoconstriction of the cerebral blood vessels, and acetylcholine, if it is released, it is causing vasodilatation in the cerebral blood vessels. Okay? So the precise role of these two will regulate the cerebral blood flow. However, under normal conditions, what happens? The vasomotor nerves do not regulate the cerebral blood flow. But normally, these are not at all important. These nerves may act indirectly by release of substances from astrocytes, which will act paracranially and regulate vasomotor tone. Okay, so these nervous regulation is acting indirectly by acting on the astrocytes. So astrocytes will release some substances which will act on the blood vessels in the brain. And in the severe hypertension, what is happening? In severe hypertension cases, what happens? The noradrenergic sympathetic nerves causes vasoconstriction and reduces the cerebral blood flow. Okay, this prevents the cerebral vascular hemorrhage and a stroke also, and it protects the integrity of the blood brain barrier also. Okay, so at high blood pressure levels, what happens? There will be disruption in the vascular bed of the cerebrum, causing hemorrhage, stroke, and disintegrity of the blood brain barrier. So this is protected by our release of noradrenaline by sympathetic nerves in severe hypertension in the brain. Whereas in severe hypotension, what happens? Acetylcholine will be released from the sympathetic nervous system only. It will act as a vasodilator, and it prevents the syncopal attack by maintaining the cerebral blood flow. So sympathetic fibers are important. They can release an adrenaline or they can release acetylcholine. Okay. So we have seen because of the obstruction to cardiac output, it may lead to decrease in the cerebral blood flow, leading to syncope, and may be due to cardiac arrhythmias such as sinus arrest, heart blocks, Stokes-Adams syndrome. So because of many pathologies in the heart, the like obstruction to cardiac output, cardiac arrhythmias, and myocardial infarction, all this will lead to cardiogenic syncope. That is because of the heart pathology, the brain is not getting enough blood supply. Then coming to the non-cardiogenic syncope, why it is occurring? It may be because of many causes. First one is a vasovagal syncope. So vasovagal syncope occurs due to vasovagal reflex causing sudden hypotension and bradycardia. Okay, so what is vasovagal syncope? Because of the a reflex. So we are not going into details. We are discussing only the headings, important points. That's all only. Vasovagal syncope occurs due to a reflex. It is called vasovagal reflex. It will cause sudden decrease in the blood pressure. That is sudden decrease in the blood pressure. That is hypotension and bradycardia. So this leads to decrease in the cerebral blood flow. And postural syncope. That is when you change the posture, the blood pressure is decreased because of the inadequate vasomotor response. Normally, when you change the posture, there is no syncope because of our vasomotor response system. But if that system is inadequate, so it leads to syncope called postural syncope. Now, third one is carotid sinus syncope or the carotid sinus syndrome. It results due to excessive sensitivity of the carotid sinus to compression. So, if you compress lightly also, like a wearing a tight collar, it is leading to syncope because it is obstructing the blood flow to the brain. It is called carotid sinus syncope or the carotid sinus syndrome. And Valsalva maneuver. So syncope is associated with the increase in the intrathoracic pressure. So the pressure in the intrathoracic area, if it is increased, there is a decreased blood flow to the brain. So it may occur during a micturition, that is causing micturition syncope, and during defecation, that is called defecation syncope, and during coughing, that is called tussive syncope. So these are the Valsalva maneuvers, that is increase pressure in the intrathoracic area. During these situations, it will lead to syncope. This is called Valsalva maneuver syncope. So these are the non-cardiogenic syncopes. That is Valsalva, vasovagus syncope, postural syncope, carotid sinus syndrome or carotid sinus syncope, Valsalva maneuver syncope. And coming to metabolic syncope. Metabolic syncope occurs in these situations like hyperventilation. So if you hyperventilate, what happens? The carbon dioxide levels in the body got washed out. Leads to hypocapnia. It results in the vasoconstriction. So it is leading to decrease in the cerebral blood flow, causing syncope. And hypoglycemia, decrease in the blood sugar levels. It impairs the activity of the VMC, that is vasomotor center. So VMC is responsible for maintaining blood pressure. Now it is not able to maintain that much blood pressure. So there is decrease in the cerebral blood flow, leading to syncope. These two are called metabolic syncope, that is hyperventilation and hypoglycemia leading to syncope. So syncope is the transient fainting because it may be due to cardiogenic causes like cardiogenic syncope, non-cardiogenic causes leading to non-cardiogenic syncope, and metabolic causes causing metabolic syncope. So in this class we have discussed about cerebral circulation. We have seen the arteries and veins of the brain and what are the characteristics of the cerebral blood flow and what is the normal blood flow, how much it is blood is flowing into the brain, and what is the normal oxygen consumption of the brain, and what is the source of energy, that is glucose, and what is the RQ also we have discussed, that is respiratory quotient. It is between 0.95 to 0.99. And how the distribution of the blood in the brain has happened, that is through central branches and through cortical branches. In the cortical branches we have seen the anterior and posterior watershed infarcts. And we came to the measurement of cerebral blood flow by four methods: KT method, SPECT, PET and MRI method. Then we have learned the regulation of the cerebral blood flow by four mechanisms: metabolic regulation through carbon dioxide, oxygen and potassium ions, and auto-regulation through metabolic theory and myogenic theory, and the role of intracranial blood pressure, how it is regulating the cerebral blood flow by Monro-Kelly doctrine and Cushing reflex, and how our nervous system is regulating, that is sympathetic nervous system, by releasing noradrenaline and acetylcholine, how it is regulating. And in the applied aspect we have seen the different types of syncopes. Our next class will be about synaptic transmission.